Hello, in this video I will talk about different ways that organic chemists represent organic molecules, from the very simple Lewis dot structure that you learned about in general chemistry, which may include lone pairs of electrons if there are atoms such as oxygen, nitrogen, halogens, and so on. Unfortunately, sometimes chemists get a little bit lazy and leave out the dots, so I will continue to refer to these as Lewis dot structures even if they don't specifically show the dots. In other words, these are structures that show all the bonds, all the atoms, everything is explicitly shown in the structure except possibly not the dots. We'll also talk about condensed structures, which are a little bit more efficient to draw. If there's more than one hydrogen on an atom, it will be, instead of showing all the hydrogens, it will be just shown once, but then there'll be a subscript to indicate how many there are. But mostly we want to talk about these line angle structures. These are structures that organic chemists use all the time. They're very simple to draw once you get the hang of it. But not so simple to interpret because they don't show any specific hydrogens or carbons. They're just represented by lines, and so we'll need to spend a little bit of time talking about those. I strongly suggest that you read pages, that you stop the video at this point and read pages 16 and 62 and look at and study the examples that on the pages that follow, pages 16 and 62. Now, here are examples of the kinds of structures I'm talking about. Notice that this structure is a good Lewis dot structure. It shows all the carbons. It shows all the hydrogens bonded to each carbon. In this particular case, there's an oxygen, and the two lone pairs on the oxygen are shown in the structure. So this is what I'd call a good Lewis dot structure. One thing to notice about this is that it doesn't show you the shapes of the atoms. In other words, this carbon, for example, looks like it's T-shaped, but of course it's not. It's tetrahedral, if you remember from general chemistry. The 4 groups of electrons means tetrahedral. Same can be said for these other ones. So in this particular case, for example, the hydrogens on this carbon are shown in a sort of a Y shape. That's only because if we drew them in a cross shape or a T shape, the hydrogens would have to be on top of each other, and that's inconvenient. So it's just drawn with dashes to show what's attached to what, but not necessarily the shape of the molecule. Notice this structure is the same, but I've left the pairs of electrons out, or the lone pairs in this case, just because that's how it's often done. You will, of course, be required to realize that there are lone pairs on that oxygen, even if they're not shown in the structure. And just to remind you, the way you know that is because we know oxygen has to follow the octet rule, and since there are 2 single bonds, there have to be 2 more pairs of electrons, and those are lone pairs. This kind of structure is what's called a condensed structure. It's the same as this, same molecule as this one, but notice that this carbon with 3 hydrogens is shown as CH subscript 3. This carbon with 3 hydrogens is shown as CH subscript 3. This carbon just has 1 hydrogen, so it's just shown as CH. This carbon has 2 hydrogens, so it's shown as CH2. Then there's the oxygen. This carbon has 2 hydrogens, so it's CH2. This carbon has 3 hydrogens, so it's CH3. You will be expected to, if required, to look at a condensed structure and be able to draw the Lewis dot structure. However, typically we're not going to do that. We will just learn to interpret condensed structures as is. Notice that this is, again, the same kind of thing. It's a condensed structure. It's just not showing the lone pairs. Again, that's very common to not show the lone pairs, although really they should be shown. Lots of times people don't show them. Now, this kind of structure is what's called a line angle structure. As I said before, it's much easier to draw. Obviously, you just have to draw some dashes and angles and so on. So let's interpret that. Notice that whenever there's an angle, like at this point, at this point, at this point, that represents a carbon. So this is a carbon right here. You don't see a C drawn there, but that's to represent a carbon. Same thing there, same thing there. Those carbons will then have as many hydrogens as they have to in order to make sure that each carbon has 4 bonds. Also, though, notice, and this is the tricky part, this CH3 is represented by the end of that stick. So right there where the red dot is, that's a carbon, and it has 3 hydrogens. It has to have 3 hydrogens in order to have a total of 4 bonds. Same thing here. That's a carbon at the end of that stick. is a carbon, and there has to be 3 hydrogens on it in order to make a total of 4 bonds. Same thing here. That's a carbon, and it has to have 3 hydrogens in order to make a total of 4 bonds. Again, this is the same thing, just drawn without the lone pairs on the oxygen. Okay, so now let's look at some actual cases, and I'll have you pause the video at a few places and see if you can draw various things. This molecule is obviously 6 carbons in a row. Each carbon has 4 bonds, and then the requisite number of hydrogens on each carbon. This particular molecule, by the way, is called hexane. We'll worry about naming compounds later on. Turns out hexane is, for example, a constituent of gasoline. It makes up roughly 2% of the compounds that are in gasoline. I've also made a model of it, so notice that we have 6 carbons in a row. They're in kind of a zigzag shape, but since those are all single bonds, we can rotate around them. So in real life, hexane molecules are constantly squirming around like a worm or a snake. But the key is that there are 6 carbons in a row. Each one, this one has 3 hydrogens, this one has 2 hydrogens, this one has 2 hydrogens, and so on. It's drawn in this Lewis dot structure simply like this. Again, the carbons don't look like they're tetrahedral in this structure, but that's okay because Lewis dot structures don't attempt to show the shapes. I'll also show you that hexane is a real thing. This is a bottle of hexane, and it says hexane right there. And if I pour out a little bit of hexane, just so you can see what it looks like, hopefully you can notice that it just looks like water. But if you were to smell it, you would definitely know that it's not water. It, in fact, has a smell sort of almost a gasoline-ish type smell, or a solvent smell of some sort. Also, if you were to set a match to it, it would burn very, very rapidly. We're not going to do that right now. Anyway, this is hexane, Lewis dot structure. This is the condensed form of hexane, so CH3, CH2, 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 CH3, because this carbon has 3 hydrogens, this carbon has 2, this carbon has 2, and so on. Now, let's see if you can pause the video for a minute and then draw the line angle formula. Okay, so let's take a look at what it would look like. There we go. Now notice that this is a carbon, this is a carbon, this is a carbon, this is a carbon, but also this is a carbon on the end, and this is a carbon on the end. So this is a total of 6 carbons. 1, 2, 3, 4, 5, 6. And you would just have to know, if you were looking at this structure without seeing these other 2 structures, that that carbon would have 3 hydrogens on it because it only has 1 bond to it. Therefore, it needs 3 more hydrogens in order to make a total of 4 bonds. This would have 2 hydrogens on it. This would have 2 hydrogens on it, and so on. This molecule may look the same, but it has, if you count carefully, 1, 2, 3, 4, 5, 6, 7 carbons. So this is a different compound. It's called heptane. Very similar to hexane, but different formula, different molecular weight, different properties, and so on. Now what I want you to do is draw the Lewis dot structure for that, and then draw the line angle structure, the zigzag type structure. So pause the video for a minute and see if you can draw those 2 structures. Okay, welcome back. Let's draw both of them. There is the Lewis dot structure, obviously 7 carbons in a row. This one has 3, this one has 2, and so on. Let's look at the line angle structure. There it is, 1 carbon. Remember, the end of a bond is 1, so that's 1, 2, 3, 4, 5, 6, 7. Here is another alkane. This also has 7 carbons in a row. 1, 2, 3, 4, 5, 6, 7. But it has another carbon attached to the center of the 7 carbons, in the middle of the 7 carbons. We'd call that carbon number 4 if we counted from this end. 1, 2, 3, 4. And it has a CH3 group attached there. So now draw the condensed structure and the line angle structure for that molecule. Pause the video. So let's draw the condensed formula. Here we go. Now notice in most condensed formulas you don't see dashes for bonds. You can always put in dashes if you want to. In this case, you have to, because otherwise, where are you going to draw that CH3? So we just draw a little dash in there to indicate that that carbon is bonded to that carbon. Now let's draw the line angle structure. And there it is. Again, just carbon at the end, that's a CH3 group, a CH2, a CH2, a CH now, because that carbon only has one hydrogen on it, and that carbon you would have to recognize only has one hydrogen on it. None of the hydrogens are shown, but you realize that there is in fact a hydrogen there. That then is a CH3, that's a CH2, and so on. Now, here is a line angle structure. What I want you to do is pause the video and see if you can draw the condensed formula and the Lewis dot structure for that molecule. So pause the video and then we'll take a look. Let's draw the condensed formula. Okay, first of all, notice that that carbon has 3 CH3 groups on it, no hydrogens. So that's that carbon there has 3 CH3 groups on it, no hydrogens, but it also has another carbon. That's that one shown there. Then that carbon has to have 2 hydrogens. So I've drawn it as a CH2. How do you know it has to have 2 hydrogens? Well, because it already has 2 bonds to it, and to make a total of 4, then it needs 2 more hydrogens. Then we get to that carbon, and it has just 1 hydrogen on it because it already has 3 bonds to it, so 1 more to make a total of 4. It has a CH3 on it, that's that right there. It's also attached to another CH that just has 1 hydrogen because it also has already 3 bonds to it, so that's just a CH. Then it has another CH2 and a CH3, and then another CH2 and a CH3. The second of those CH2, CH3s I've shown with a dash there to show that it's attached to this chain, but not in the chain. Same with this CH3 and same with these 2 CH3. So there's your condensed formula. Now, draw condensed structures for these molecules. This will take you a few minutes, but if you've learned the rules, you should be able to draw condensed structures for those without too much trouble. So pause the video and do that. There's the condensed structure for that molecule, another CH3, CH3, CH, CH, CH2. So that CH2 is this carbon right here with 2 hydrogens. There's another CH2, that's that one. There's a CH3 on the end. Sorry, that should be a CH3 there. That was a typo, my mistake. That's C with a CH3 on it, a CH2, and another CH3. This one, let's look at its condensed structure. CH3, CH2, that's that CH2, another CH2, and then a carbon with no hydrogens on it because it already has 4 bonds. That single bond, and 2 bonds and a double bond. So that's that carbon with no hydrogens, but it has a double bond to it. And notice that in this case, right in line, we do show the bond because we need to clearly show that that's a double bond. So we put that in there explicitly. Then next we have a carbon with 1 hydrogen. That's that one. A carbon with 2 hydrogens and a carbon with 3 hydrogens. Now let's look at this one. It's a little different because it has a ring. Now you see in this condensed structure we have dashes shown all over the place because really the only way to do a condensed structure for a ring is to show the specific bonds between the members of the ring, but notice that this CH2 is that carbon right there, and it has to have 2 hydrogens because it already has 2 bonds, so it needs 2 more to make a total of 4. That carbon has no hydrogens on it because it already has 4 bonds. That carbon has 3. That carbon has 3. This carbon has 1 because it already has 3 bonds. Same thing here, and then this is CH3 and CH3. Notice that in the structure I could have just typed that as CH3, but I chose to show it specifically as a separate group with a dash shown here. The reason I did that was because I wanted to show that that CH3 and that CH3 are the same as each other, but it would be perfectly acceptable to just type that as CH3 and leave this dash in that group. Now, here are some more complicated condensed structures. Try drawing them as line angle structures. That would be a good quiz for you. Also, try drawing a variety of line angle structures. Just go crazy and draw dashes and angles and stuff all over the place. Just make sure you don't have more than 4 bonds to any particular point in the structure or any particular carbon atom. And then convert them to condensed structures. And this is all just for practice. And finally, practice with other structures you find in the book and online. Again, just go all over the place, Google organic structures, and you will find all sorts of line angle structures, and you can practice drawing them as condensed structures and vice versa. Thank you.